Hello. Welcome to the class. How's everyone doing? Hope everyone had a good weekend. Got some people in the chat asking what the music is. That's from Donkey Kong Country. I'm actually going to switch up the music next class, I think. We'll have some different music going forward. I've been kind of lazy with switching up the special effects. All right, so last class, last Thursday, I introduced assignment 2, in which we're making a Geometry Wars clone. And you've got 2 weeks to do that. So next Thursday, that'll be due. Not the one coming up, but the Thursday next week. And what we're doing now is we're starting to go forward looking into assignment 3. And so the things we're going to need to learn in order to be able to do assignment 3, we're going to talk about today. We're going to talk about collision detection and collision resolution. And we're going to be talking about different shapes like rectangles, for example. Last time we did circles. The next class, we're going to talk about how we're going to be doing sprites, textures, and animations in the course. That'll be pretty interesting. Then next Tuesday, we've got midterm break, so there's no lectures next Tuesday. I may still stream next Tuesday, so feel free to tune in. Maybe I'll do some programming or something like that, but there won't officially be a lecture. It won't be on the exam. And then after that, we'll talk about game event systems and replays and how we would implement stuff like that. So that actually is a new lecture to this year of the course. It wasn't in there last week. And if you happen to be tuning in on last Saturday night, actually, I was streaming some programming. I was doing a lot of this game event stuff during that stream. So that should be fun. So let's get right into today's lecture then. We're going to be talking about collision detection and resolution, as well as axis-aligned bounding boxes. So we'll figure out what those are called. And if you've done any sort of game programming, you may have seen the term AABB before. And so that's what that is. And we'll get into that in a little while. So when we talk about collisions in games, collision programming involves 2 separate stages. The first stage of collision programming is collision detection. So given 2 moving entities with some given shape or bounds, determine if they intersect. And collision detection is a geometric problem, so it deals with a geometry of different shapes. Collision resolution is the second stage, and collision resolution, we talk about, okay, now that we've detected that 2 entities have actually collided, what we want to do is actually determine what the results should be. So how do we resolve the physics of this simulation? So I want to, real quickly, go over something here. So if I go back to this, so this is what our assignment will look like, okay? Now, there won't necessarily be NPCs. Why can't I control this? I died. I died in the game that I created. Oh, yeah, okay. So NPCs in this game will be a bonus feature that you can implement if you want, but I've just put them in there. So, for example, in this game, we're controlling this Mega Man character who's running around the screen. This is assignment 3, by the way. This is what you'll be creating. And so the Mega Man character or the Mario character or any 2D platforming type character, you want to be able to do things like, okay, I wanted to determine whether I'm colliding with the ground. And if I'm colliding with the ground, I want to stay on top of the ground, right? So the first check would be collision detection. Am I colliding with something? And the next one is collision resolution. So once I've detected a collision, what do I do? So for example here, if my character is colliding with the ground, and in this engine I can actually... let me load up one other thing. So, okay, this is the actual assignment that we'll be working on with no enemies. But the reason I loaded this up is because we can actually toggle the drawing of textures, so I can turn on or off the drawing of textures, and I can also turn on or off the drawing of collision boxes, okay? So here, we can see the game sort of from the physics engine's point of view, where there's no textures being drawn, but we can see all of the different collision boxes. And this is just one of the options in the user interface that I'm giving you, is to be able to turn this on or off. So for example, here we can see that we're standing on top of this box, and then we slide down and we're now standing on the ground, right? So if I draw both at the same time, you can see that these two boxes are colliding, then I slide off and I stand on the ground. So detecting collisions and resolving collisions are different. And a good example of that is right now I'm just standing on the ground, but let's say I detect a collision from below with a brick. Then what happens is I actually want to destroy that brick. Or if I detect a collision from below with a question mark, then I want to do something to the question mark and maybe spawn the coin above it, right? So if I collide with the question mark from above, nothing happens, but from below, something interesting happens. Similarly, we have bullets that we can fire. Those bullets have a collision box, right? We can see this. And if those bullets collide with bricks, then we want to be able to shoot and destroy those bricks. So our games are going to have some sort of mechanics centered around different things colliding with different things. And so that's the incentive for this lecture, if it wasn't, already obvious from people who play video games. So let's get back to the lecture now that we've kind of shown what we're working towards. So we've got these two distinct steps. We've got collision detection, which is detect when a collision occurs, and then collision resolution, which is what should happen once that collision is detected. So just some assumptions for these slides. So we're operating within the course definition of entity, and we're going to assume that collisions are going to be occurring between entities that have the following attributes, or in our case, these entities are going to have the following components. So the entities are going to have a position component, right? They've got to have an XY position. They have some sort of bounding shape. So one example might be a circle bounding shape for assignment 2, a rectangle bounding shape, which we'll have for assignment 3, or maybe in the future we'll have some more arbitrary line-based bounding shape. And they also have some sort of velocity, right? Because if two things don't move, then they can't become intersecting. Well, I guess they could be spawned on top of each other, but that's not really an interesting case. We're interested with moving things that are colliding with each other. So our goal is to learn the mathematics that allow entities to interact with each other in the game in interesting ways, so that we can take those interactions and form them into game mechanics somehow. So there's different types of collision detection problems. One of them might be this case. So given two entities which have a speed, a position, and a bounding shape, determine if, when, or where they will intersect. Okay, so that's one problem. We want to determine if they'll intersect. We might want to determine when they will intersect. And we may want to determine where they will collide, right? So these are all different problems. So for example, we may want to determine okay, maybe they'll collide here. Or maybe we just want to determine whether or not they're already colliding or something like that. So here's the problem that we're going to be dealing with in the course, is given two entities which have a current position, do they intersect? So that's going to be the first thing we do today. So for example, this blue rectangle and this red rectangle are currently intersecting. The red rectangle and the green circle are currently intersecting. The purple circle and the red rectangle are not intersecting. So given some shape with some properties, are they intersecting? And also something that we're going to want to have is that given two entities which have a current position, what is the current overlap? Okay, so not only, for example, are the red rectangle and the blue rectangle intersecting, but what are the dimensions of their overlap? And that's going to be very important going forward. Because when it comes to the collision resolution stage, we need to know more information than just, are they intersecting? We need to know where they're intersecting and by how much they're intersecting. So we've talked a lot about these bounding boxes, bounding shapes. What are these things actually? So in the real world, objects can have arbitrary shapes or interaction surfaces, right? So let's see my hand, for example, right? If I take, what can I take here? Let's take my phone. My phone can interact with like arbitrary points of my hand. Like this is real world physics, right? The bounding boxes can be arbitrary. They can be three-dimensional. They're really, really precise. But completely arbitrary, real valued collision boxes are difficult to store, they're difficult to compute, they're difficult to simulate accurately and continuously. And so when we talk about computer simulations, and by computer simulations oftentimes we mean video games, they must be made of some sort of primitive type, right? And so, for example, we could have two-dimensional objects such as lines, triangles, circles, rectangles, or we could have 3D shapes such as spheres, planes, cylinders, prism, etc. So if you want to model my hand, maybe you'd take my fingers as like different cylinders that have joints. Maybe my hand is a plane or something like that. And so the bounding shape concept is that we're going to simulate the interaction bounds of a complex shape like my hand with a simpler one. Right? So we can't hope, especially in this course, to create a completely arbitrary universe physics simulator. And so we're going to abstract the concept of these complex shapes with simpler ones. So let's say, for example, we have the case of Mega Man over here, or we have the case of assignment 2, we have an octagon for the player, right? So in one case we have an octagon, in one case we have Mega Man. So what we're going to do is we're going to create shapes that sort of closely resemble what you would intuitively think of as the bounding box or the bounding shape or how things would interact with this. So, for example, if we did have an octagon, then a bounding shape we might want to use, which makes it easier for us to calculate things like collisions, would just be the circle that which is it circumscribed, it's called? So anyway, the circle which is touching all the points of the octagon. So the octagon is inscribed within the circle, whatever the mathematical term is. For Mega Man, for example, we might not be super interested in like all the different limbs and all the joints and all the hands. So let's just draw a box around Mega Man and say that if something interacts with this box, then it is interacting with Mega Man, right? That's a pretty safe assumption that people have been using for decades when it comes to game programming. So the simplest 2D bounding shape to store and compute is a circle with a given radius, right? We saw that, where we had one circle and another circle, and we just did the very simple math, which took the distances between the circles, and if the distance between the circles is less than the sum of the radii of the circles, then it's colliding. And so we talked about that in the last lecture, so I won't cover it again. But other bounding 2D shapes can be constructed with a number of line segments. So for example, the simplest of these would be a rectangle. And the simplest not in terms of the number of sides, but the simplest in terms of computation. So what we're going to be dealing with in this course for 2D shapes are bounding rectangles, or they're also called bounding boxes. So let's talk quickly about the bounding box size. So most 2D games use rectangular sprite graphics. And so for example, over here, you have a part of an animation frame where Mega Man is running. And Mega Man running here is going to be stored in some texture data somewhere. And those textures are going to be drawn as sprites in our game. And those sprites, so the rectangular images that form the sprites make a natural fit for the rectangular bounding box. And usually, what we'll do is we'll say that the bounding box for collisions will be the smallest rectangle that encloses the sprite. And so what we can do usually is just say, okay, we have some texture size to draw our sprite with, and so the bounding box is going to be the smallest rectangle that fits that sprite. That's it. And usually, that's going to just be the texture size. So for example, if we have a texture that's maybe 64 pixels by 64 pixels, then our bounding box would be of size 64 by 64. But sometimes that is not the case. So for example, here are some cases where that works really, really well. So we have a brick texture from Mario, maybe who have a question block, or a pipe, or a block that you can't break, or even Mario themselves. All of these things fit really well into that singular, like square-shaped rectangular bounding box. But sometimes that's not the case, and it could be caused for a number of reasons, but I'll just give you one of those cases. So sometimes the bounding box doesn't fit the exact bounds of the image or the texture that we've drawn to represent these things. So for example here, let's look at Mega Man standing, okay? So Mega Man standing has a different vertical size. So if I draw this out like this, and I draw this out like this, we can see that the vertical size of Mega Man's standing texture or standing animation is smaller than the extended jumping animation for Mega Man. Now, ideally, what we want to do when we store textures for a video game is that all of the textures for a given sprite will be stored in images of the same size. And so in order to store images of the same size, your image has to be approximately sized to the largest dimension of any of the images, right? So if we see all of these different examples here of running animation, jumping animation, standing animation, then we're going to take the size of the jumping animation to be the size of our texture, because we have to fit all of that jumping animation in there. And so in this case, we have an example where the size of the texture should not be the size of the bounding box. And the reason for that is we don't want bullets that pass through like right here to be considered colliding with Mega Man. So what we usually want to do is we want to take a little bit of a smaller collision bounding box for the entity rather than the larger bounding box for the entity. So here, for example, we can make a custom-sized bounding box which is different than the texture size. And so, for example, when Mega Man is standing, this texture size, now it just so happens that if these rectangles are like, if the textures are 64 pixels by 64 pixels, then this bounding box works out to be about 48 pixels. All right? So about like 80% the size or something like that. So what will happen in the game is that this whole texture will be drawn, but only within the red bounding box will the collisions actually happen. All right? So for example, if a bullet hits maybe the top couple of pixels of Mega Man, he won't end up dying. And that's because we've got a custom-sized bounding box, which is not necessarily the same size as the texture. All right, so that's one of the use cases where we would want to do that. And not only that, but let's say you think that the game is too difficult, and so what you could do is you could maybe resize the bounding box to be something really small so that you could fit, like the player wouldn't be being hit by as many bullets. And you'll see these, like we talked about a little bit last time, about these bullet hell type games, or like top-down shooter type games where there's so many bullets on the screen, you actually want to shrink the bounding box of the player so that the game is a little bit more forgiving. Cool. So axis-aligned bounding boxes, or AABB, what are those? Well, rectangles in a 2D plane, like if we're talking about arbitrary geometry, we can have a rectangle that takes any orientation, right? The only thing that defines a rectangle is whether or not there's a right angle at all four corners. So a rectangle is defined as a four-sided shape whose internal angles are all 90 degrees. But they could have like some arbitrary angle, like right here from the axis, right? This theta could be whatever it wants. But determining the intersection of arbitrary rectangles can be a little bit slow, and it involves computing all the different line intersections, right? So, and we'll learn about this later in the course, how to do line-line intersections. But it turns out that even though it may seem more complex at first, it's actually easier to detect whether or not two bounding boxes that are axis aligned intersect than it is to tell whether or not two line segments intersect. So we'll talk about line segment intersection later, and so that then we can do arbitrary orientation rectangle intersection. But before that, what we're going to do in this lecture is just talk about axis aligned bounding boxes. So by aligning our rectangles with the X and Y axis, we can trade the precision of arbitrary alignment checks for very fast intersection and collision text. And so since if we think we have we have an axis here, an X and a Y axis, then if our bounding box is aligned with those axes, we have an axis aligned bounding box, or AABB. All right. So what sorts of checks can we do with these AABB, with these bounding boxes? So the simplest possible collision check we can do is to see if a single point is inside the box, right? So in order to define a rectangle, I need a certain amount of data. And so one of the ways to define a rectangle would be to define the upper left-hand point. So here we have x1, y1. That's the upper left, or the top left point of the rectangle. And down here we have the bottom right point of the rectangle, or x2, y2. And then we're going to have a point that's defined by its x and y coordinates, and we'll just call that x1 and y1. Now, this drawing on the screen here has a width and a height. This circle is not an infinitely small point, but we are talking about points here, right? So there's no width or height when we're talking about this point. Oh, excuse me. Okay, so how do we determine if this point px, py is inside this rectangle? Now, I'm sure you could all, determine this, and you could all figure out axis-aligned bounding boxes on your own. But let's go through it just in case there's any troubles with that. And we'll also talk about some optimizations of how you could make those checks faster as well. So, P is inside the box if the following conditions are true. If Px is greater than x1, right? So it has to be right of the leftmost side. If Px is less than x2, so it has to be less than the rightmost side. If py is greater than y1, so it also has to be below the top. And I'm sure you can all guess what the next step is. It also has to be above the bottom. Right? That's pretty obvious. So, another way that we can represent a rectangle, and this is the way that SFML actually does it, and most graphics libraries do, is instead of defining the top left point, right, and the bottom right point, what it does is it'll define the top left point and a width and a height. And so that's how we're going to do our math. And if we translate that last slide into this form of a rectangle, then P is inside the rectangle if Px, again, is greater than the left-hand side. If Px is less than x plus the width, right? So we figure out this x right here, which is x plus width. Py, well, Py is inside if Py is greater than the top. And similarly, Py is inside if it is less than the y value plus the height. And so to get this value, this is y plus h, right? And so I got a question in the chat, which is faster. And so let's just look at which might be faster, right? So if we have stored all of these values, then in the very simple case of just checking to see whether or not one point is inside a rectangle, then here we have just 4 if statements looking up 4 values. And here we have 4 if statements, but we also have 2 additions. Okay? So you may say that theoretically the previous one is faster, but in actual fact, like, these additions are just going to be pipelined and probably almost instantaneous. But what you could do, if you really want to know which is faster, this is the test that you could do on your system. You could say, I'm going to do 1 billion different point inside axis aligned bounding box checks, and I'm just going to set up 2 functions and I'm going to time them both. And so that's one way of doing it empirically. And empirical tests are often better than theoretical tests when it comes to implementation. Excuse me. And at the end of the course, we're going to talk about things like cache coherency and stuff like that, which makes basically everything that you've learned in computer science not matter. But we'll save that for later. Okay. So now let's talk about how do we do the intersections of bounding boxes themselves, okay? So the next step is to determine if two axis-aligned bounding boxes intersect anywhere. So, right here, we have two axis-aligned bounding boxes that intersect. And we looked back here at how we can tell if a point is within a bounding box, right? So you may think, okay, what's the naive way of telling to see of checking whether or not one bounding box is inside another? Well, one way of doing that could be, let's take all 4 points of one rectangle and see if they're inside the other one, right? Because if the rectangle is inside the other one, then one of these points must be inside it. And you say, oh, well then, okay, in order to check, then I'm doing 16 if statements. Done. Well, let's see if we can do better than that, okay? So yes, that is one way that you can do it, and you can implement that, and it will work, and you can make your game. But let's see if we can do better. So first, what I'm going to do is I'm going to separate the overlap into horizontal overlap and vertical overlap. So what I mean by horizontal overlap here is if I have two boxes and I draw a straight, well, ideally a straight line, but apparently I can't draw a straight line. If I draw a straight line in the x direction, then if that line intersects both rectangles, then there's a horizontal overlap. And so if we think about how we can detect horizontal overlap, there's a really efficient way of doing that. And horizontal overlap occurs if the top of each box is higher than the bottom of the other box. That's really interesting. So it says that if the top of this box is higher than the bottom of this one, and the top of this box is higher than the bottom of that one, then I have a horizontal overlap. Okay? So let's have a look at that. So if I have two rectangles with their top left corners x1, y1 and x2, y2, and each of them have a width and a height, so I have w1 and h1, w2 and h2, then there's a horizontal overlap if y1, which is the top of this one, is less than y2 plus h2, right? So y2 plus h2, so that's here. If this is above this, okay? Now, remember, I'm using less than in this case because in our SFML, 0, 0 is in the top left, right? So since 0, 0 is in the top left, we want this one to be less than this one, and we want this one to be less than this one, okay? So above is actually less than when we're talking about our graphics library. And similarly, if y2 is less than y1 plus h1, and so look at that, we can determine horizontal overlap in just these two if statements. So we're already doing better. Same thing for vertical overlap. Let's draw a vertical line, and there's a vertical overlap essentially if this vertical line touches both rectangles. So vertical overlap occurs if the left side of each box is less than the right side of the other box. So the left side of this one is less than the right side of this one, and the left side of this one is less than the right side of this one. Okay, so the same thing we had last time, except now, if x1, which is right here, is less than x2 plus w2, and if x2 is less than x1 plus w1, there you go, right? So that's how we detect vertical overlap. And now we can say that two axis-aligned bounding boxes intersect if they overlap both horizontally and vertically. So they overlap horizontally and vertically if this is true, okay? Now you can think if x1 is to the left of x2 plus w2, if x2 is to the left of the right-hand side of green, and if the top is above the bottom for both of them, okay? So we have these just 4 if statements to determine overlap. So, and we have some additions in here as well, right? So if we were storing it in the other way, then maybe we wouldn't have these additions, but it all kind of evens out in the end. And so what we've done is our first naive way of maybe checking all the different corners of being inside. If we reframe the problem and think about it a little more cleverly, we can end up with much more efficient algorithms for doing the same task. Okay? So as before, if we checked every corner, each corner had 4 if statements. And so we thought, well, we can do this with 16 if statements, but it turns out that we can do it with only 4 if statements. And it turns out that if statements are one of the most expensive things we can do in computing, and so we want to minimize those as much as possible. So the additions are way faster in practice than the if statements. So now we know if 2 axis-aligned bounding boxes are intersecting, but it doesn't tell us by how much, right? It just says it's a Boolean check. Is there an overlap? And so what we're going to do in our game engine is we are going to be using the center of rectangles, so the center of entities as their position. And the reason for that will be obvious a bit later. So why not just take the top left? Well, it turns out if you use the center, then a lot of the math gets really a lot easier. So how do we calculate the overlapping area for centered positioned axis-aligned bounding boxes? So that's what we're going to talk about now. So here we have our axis-aligned bounding box. And if we translate this into our actual game engine that we're going to use for assignment 3, and we're talking about the different components as well. Oops, let me move my camera here. All right. So up in the top here, we have exactly how this rectangle is going to be represented in our game engine that we're building for this course. So the position is the XY position, and that's going to be given as the center of the rectangle, okay? And we have a bounding box size, which is going to be given as an X and a Y component. So over here, we're going to show the component representation of those. So in assignment 3, our transform component is going to have a position. It's also going to have a previous position. We'll talk about that in a sec. It's going to have a scale, and we'll talk about the scale a bit later. And it's also going to have, this should be velocity, but it's the speed in the X and the Y direction, which is the velocity, okay? So then the bounding box is going to have 2 components to it, or 2 variables inside it. It's going to have the size, which is the full X and Y size of the bounding box. And we're also going to store what I'm going to call the half size. And what that does is it just computes and stores size.x over 2 and size.y over 2. Because it turns out that when we start to store our entity position by the center of the rectangle, we can save a lot of dividing by 2 if we end up also storing the half size. And we'll see how that works out in our math. Okay, and again, the half size here is just the X component, or the X direction of the bounding box size and the Y size of the bounding box divided by 2. Okie dokie. So let's see now if we can tell how 2 axis-aligned bounding boxes are overlapping when we have this centered representation, and not only if they're overlapping, but by how much they're overlapping. All right. First thing we're going to do is we're going to compute the difference in the X value between the positions of the 2 entities. Okay, so we take the X value of both and we subtract them and we take the absolute value. So dx, or delta x, or difference in x, is going to be the absolute value of x2 minus x1. All right, and the reason it's the absolute value is because we want to do these calculations such that we don't need to know which x2 or x1 is on the left-hand side or the right-hand side. We want it to work out no matter what side they're on. Okay. Also, we have these values as well. So we have this width 1 divided by 2. That's our half size that we talked about. So width 1 divided by 2 is this length right here. And in this case, it's half the width of the green rectangle. So from the center out to the right-hand side of the green rectangle. and we have the same value, but it's for the red rectangle. So if we start in the center and move out in the x direction until we hit the distance, that's the width over 2. So this starts to look like something we can work with now, right? Remember how when we had the circles, we talked about the distance between them and the radius? Well, this is going to be an almost identical calculation. So if we take this green segment, this red segment, and this black segment, then we're left with this. And now we can do a calculation here. So you can see here that we have two cases. One where the sum of these lengths are less than dx, and another where the sum of them are greater than dx. And if we go back to this slide, if the sum of these two was greater than dx, then the two rectangles would be overlapping, right? And so that's what we can use to do our calculation here. So we have an overlap in the x direction if this formula, so w2 over 2 plus w1 over 2 minus dx. If that value is positive, then we have an x overlap, right? So we sum the length of the red line segment and the green line segment, and if the sum of those two minus dx is positive, it means that it was bigger, and so that we have an overlap. And now we do the exact same thing, but we do it with the y direction instead of the x direction. So the difference in the y's is the absolute value of y2 minus y1, so that gives us the y direction difference. And now we take the height difference, okay? So we're going to take h1 over 2 and h2 over 2, and we'll do the same thing. So in this case, we would not have an overlap, but in this case, where the sum of the lengths of half the sides are greater than dy, then we would have an overlap. So we're going to sum these h1 over 2 and h2 over 2, and so we have an overlap in the y direction if h1 over 2 plus h2 over 2 minus dy is positive. Okay? Now, if we then want to find, so this tells us if there's an overlap. But now we're going to compute what the magnitude or size of this overlap is. So, now what we're going to do is compute this and store it in a vector. So, we have delta. So delta is our dx and dy. It's our delta vector. And it's going to have an x and a y component. The x and the y component is going to be the dx and the dy that we just saw. So the dx is the absolute value of the difference of the x values, and the dy is the absolute value of the difference of the y values. Then we're going to have ox. This is the overlap x. So this is how much it's overlapping in the x direction. And we're going to have oy, which is how much it's overlapping in the y direction. So here, ox is equal to w1 over 2 plus w2 over 2 minus delta x. We saw that calculation on the last slide. And then we do the same thing with the y direction. So oy is the height 1 over 2 plus the height 2 over 2 minus delta y. And then we combine those, and now we have an overlap vector. Okay? So the overlap vector is how much the two rectangles are overlapping in the x and the y directions. And if both of these values, ox and oy, if they're both positive, then our two rectangles are overlapping. See how that works? And you might say, oh, but we're dividing by 2 a lot in here. That might be a little bit expensive. Yes. But if you looked back, right, our component is actually going to store these values. So the half size x and the half size y, that is w1 over 2 and w2 over 2. And so we've pre-computed those to save. So these values will all be pre-computed, and we'll use a little bit more memory to save on all of those computations. So again, if ox and oy both have positive values, then we have an overlap of the two rectangles. And we also have computed by how much they're overlapping. Now, okay, now we've detected that. So we've detected that an overlap exists or not, and if it does exist, how much is the overlap? So now we have to talk about how we actually resolve those collisions. Excuse me. So like I said, now that we've detected the AABB collision, what do we actually do? And so the answer to this is it depends, right? The resolution of collisions depends entirely on what the physics of my game world should do. So just for example, if the player collides with a tile, maybe we want to make it so that the player cannot enter the tile, right? So maybe if it enters the tile, we want it to be pushed out so that it's no longer inside the tile. Okay, just had a quick question, with today's computing speed, is the pre-computation even still an advantage over additional memory accesses? Yes, in the case of just storing one more vec2, so 8 bytes, it ends up being faster than doing these divisions all the time. And the reason is because all these values are cached, and so the memory access is very, like, the speed of a cache hit in looking up a memory access is still faster than a division by 2. Okay, so let's take the example where a player collides with a tile. Okay, so in this example, we're going to have the following happening. This is a tile. So this is maybe a pipe in Mario, or this is going to be a brick or something like that. It's some part of the world geometry that when the player runs up against it, we want it to not enter it, right? We want it to be stopped by this wall. And over here, we could have the player, or maybe it's a bullet, or maybe it's an enemy, or whatever it is that we don't want to enter the wall, right? So here, we've got the bounding box that surrounds our player, right? And we don't want this player to be able to enter this wall. So here's the position on the first frame, and let's just say that this player is moving to the left. And so the entity with this bounding box is moving to the left, and eventually it's going to collide with this tile. So what we can do is the following. Well, on the second frame, it's here. The third frame, it's here. The fourth frame, it's here. And on the fifth frame, there's a collision detected, right? Because unlike the real world, so if my hand slowly moves toward my other hand, right? It's a continuous value. It's going to be, like, the collision is going to be really smooth. But in the video game world, we're moving by a set amount of pixels every frame. And that value is often going to be more than 1. So we're going to be moving. On one frame, we're not going to be colliding, and then on the next frame, we will be colliding. And there may be an overlap of a significant amount or by a tiny amount, but we have to now resolve this. So here, we've detected that there's a collision, right? And now what we said was the player should not be able to enter the tile, right? And the tile shouldn't move. Like, this is an immovable object. And so what we want to do in order to resolve this is maybe we'll say, okay, now that the player has overlapped with the tile, we're going to push the player back to the right by its overlap. And what we'll be left with is exactly what we want, which is the two things touching, but not actually being inside each other, right? So here's what actually happens. We keep moving. We detect an overlap, and then we push it back out. Now, you may say, yeah, but when I'm playing the game, I don't see it being pushed back out. But here's what actually happens in our game engine, if you remember. We're going to do the update step first, and the update step is going to call, for example, the physics, and then we're going to do the rendering. And so when we move the player, do the rendering. Move the player, do the rendering. Move the player, do the rendering. Move the player, but now what we do is we resolve the collision before we do the rendering. And so the player of the game never sees the step where the entity was actually colliding and inside the object, but it did happen. But we just resolved that beforehand. Okay. Then on the next frame, maybe we collide with it again and we push it back out. right? And the next frame we collide with it again and we push it back out. But we do all of that resolution before it gets rendered to the screen. Someone had a really good question in the chat, and they said, so what if your speed is so high that you travel a distance greater in one frame than the bounding box? And what you have just described is how every out-of-bounds clip happens in every video game, okay? And so we're going to talk about that in the future. And at the end of the lecture, I actually have a few videos from YouTube that talk about that as well and how it actually happens in video games. But if you're talking about so the question was, what if I'm right here on one frame, and then I'm here on the next frame, and then I'm here on the next frame? Well, it turns out what happens is you pass through. And what's going to be one of our solutions in the future that we'll talk about is what you can do is instead of doing jumps by this big, and I'm getting way ahead of myself here, is that instead of like moving by this many pixels one time per frame, we could move by, say, this many pixels several times per frame, right? So we could still have the same visible speed, but we just do more frequent, smaller updates. And so that's actually what a lot of video games end up doing. All right, so that's one issue of, or one possible case of resolving collisions, and it's the easiest possible case, right? Where we've collided with a wall by some overlap and we just push ourselves back out. Cool. Here's a trickier resolution case. What if, again, we have an immovable tile right here, and we have a moving player, and this player is going to be moving to the left. So on one frame it's here, next frame it's here, next frame it's here, next frame it's here. Okay, so collision detected. What did we do? Uh-oh, this is actually a little bit trickier, right? Because now we have options. So let's see, what did we do on the last time we did this? Well, we had an X overlap, right? So what we did was we pushed it back out to the right by that X overlap. But now we have a Y overlap as well. And so, okay, let's just say what we do is we're going to do what we did last time and just add the overlap, right? But that's kind of bad physics, right? If we look at what happens here, then it goes left, 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 and then it jumps right up here. And that's maybe not what we want in the game, right? So, what's another option? Maybe we want to just move up, right? So we moved all the way to the left. Maybe we're just going to push it up. But the issue is that we came from the right. We didn't come from the top, right? So what do we do here? Here's another possible situation. Oh, so this is what would have happened if we move up, is we go left, 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 and then we appear up on top of this thing. So maybe that's what we want to do. I'm not sure. Another option is push it out to the right. So for example, if I'm moving left, 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 then I want it to resolve here, okay? So for example, in the real world, if I have two objects like this, and one of them moves into the other, it's just going to stop right there. So that's the option that I have on the screen. Maybe in a video game, if I have stairs or something like that, I actually do want it to slide up on top of the other one. So here's a case where now we're going to learn the math behind all of the different possible resolution cases, and then in your video game, you are going to decide which of these resolution cases you actually want to implement. And in our assignment, I'll tell you exactly which one I want you to implement. Okay. So when detecting collisions in our game, they will first happen on a specific frame. And so what that means is the frame before the collision is detected, there's no collision, obviously, by definition. And then on the frame that there is a collision, there will be a collision. So what we could do is try to use the overlap to detect which direction the movement came from. All right? So let's try and use the overlap to determine the direction of movement. So here's a possible case where we have this overlap here. So how do we know which direction the green block came from in order to resolve our collision? Well, the green block could have come from the Y direction, or it could have come from the X direction, okay? And one of the ways that we can solve this problem is to use the previous overlap to detect the direction. Because if all we do is have the overlap, if it has an X and a Y component, then we can't tell where it came from. So what we can do is use the previous overlap. And I'll talk about other ways of doing it later, but I'm just going to use this for now. So what this means is if the previous frame's overlap was greater than 0, so if the previous frame's overlap in the Y direction was greater than 0, then the movement came from the side like this. So here we have a Y overlap greater than 0. We don't have an X overlap, but we have a Y overlap greater than 0. And so we know then that it's coming from the side. And so we could resolve this one by pushing it out to the right. So that's what we would do. If, however, the previous frame's overlap's X component was greater than 0, then we know we have one of these overlaps. And so we could resolve the collision by pushing it in the Y direction. Okay? So if we're moving downwards, here we had an X overlap, but no Y overlap. Now we have both. So on the previous frame, there was an X overlap greater than 0. And so what we can do here is push it in the Y direction of the overlap. Okay. So now that we know whether it came from a side or from the top or the bottom, now we can actually do things like top or bottom detection. So a collision came from the top if it had a previous overlap's X value greater than 0 and its Y value is higher. Okay, so here I say higher, but in the game engine where we have 0, 0 in the top left, it would actually be lower. So just keep in mind that. And we have a bottom collision if it had a previous overlap of X greater than 0 and its Y value is lower. Okay, so this means that it would come from the bottom. So in our game, we do have a case where we are trying to detect, like if we have a question mark block, if the collision is from the top, then nothing happens. But if the collision is from the bottom, we want to spawn a coin, okay? And I see a number of people in the chat suggesting other ways. There are a million different ways to do this, right? When I started this course, I'm saying this is just one way, and I've chosen a way to do it, which is a balance between usability, understandability, and optimizations. Okay. And for all people asking questions in the chat, go back and watch the rest of the lectures, okay? So this is lecture 8, and I don't have time to explain all the other lectures. So it's great that people outside the course can watch the lectures, but if you have questions, first go back and watch all the other lectures, because most of these have been answered. There's one tricky case, however, okay? This is a really tricky case, and you've probably all been wondering what's going to happen in this case. What if the previous frame had no overlap in the X or the Y direction? So what if it's moving diagonally? Okay, so we go diagonal, diagonal, diagonal. What happens now? So we must decide on how to resolve collisions based on the previous position and overlap size. So for example, what you could do here is say, well, once I have overlap, well, there was no X or Y overlap, so maybe I'm going to push it out in the direction of the most overlap or something like that. So we have to choose in this very specific, very tricky case. We just have to decide what we want to do, play test the game. If it feels right, use it. If not, then don't use it. What if an entity overlaps with multiple entities, right? So let's say that in our game, a wall is going to be represented by a stack of different tiles, for example. So what if our entity overlaps with multiple ones? So here, for example, we're going to move, 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 and now we're overlapping multiple ones. And the order of the collision checks may actually matter here, okay? It could be a little bit tricky. The previous overlap method that I discussed, it usually resolves this case. But using the previous position only doesn't. So when some people are saying, for example, oh, just use the previous position, you don't need the previous overlap, this is a case where that may not work, okay? So we're trying to solve all possible cases for our particular assignments that we will be implementing in this course. So, important note, all of the collision resolution discussed here is for the simple case of avoiding overlap. So this is useful for cases, for example, when you're walking on tiles, when you're walking into a wall that you don't want to be able to intersect, when a bullet hits an entity, all that kind of stuff. But there are many, many other kinds of collision resolution, right? Let's say, for example, that we have a kinematic elastic object or an inelastic collision where we actually have like a pool ball bouncing off the side of a pool table or something like that. How would we resolve that? Well, it's a lot different than what we're doing in this case when we're just like avoiding the overlap. And you may have a physics simulator, and that physics simulator could have mass, it could have different forces. And so, depending on the game, right, if you're writing a different game than we're writing in this assignment, you will not be using these formulas. You may use a completely different formula. Okay. One thing I want to note here, just as an example of how you would do something differently than we're doing it in our course, and it may end up actually working out better. So if you've played, tell me in the chat if you've played the original Super Mario Brothers. I'm sure everyone has probably played the original Super Mario Brothers. So the original Super Mario Brothers, in order to save on computations, did the following. It operated differently than we've presented here in this course. So it considered the case. So let's just talk about the case where Mario wants to jump on top of an enemy, right? So Mario can jump on top of a Goomba and kill it. It can jump on top of a Koopa and kill it, or a Hammer Brother. There's lots of different things that Mario can jump on top of. So what the Mario engine actually does is it computes the AABB Boolean, is there an overlap? So as Mario is jumping along, the game engine is computing, does Mario overlap with a Goomba, for example? However, instead of trying to determine like the previous overlap and do all the complicated stuff that we did, what it does is it says Mario kills the enemy if he's moving downward. No matter what the X direction is, or the relative X and Y positions between the enemies, if Mario's Y velocity is negative, so if he's moving toward the ground, he kills the enemy. So let's look at an example of that. So here's Mario. Normally, what you do in order to kill an enemy is you jump, you take some sort of arc, and you land on top of the Goomba, right? So the Goomba has a bounding box, Mario's going to have a bounding box, and so the first check is, do these bounding boxes actually overlap, right? So is there an overlap here? So on this frame, there wouldn't be, but maybe on the next one, Mario collides. And so if you took our way of doing that, then the bottom of this bounding box hitting the top of this bounding box would be the only way for this Goomba to die. But it turns out, in the actual Super Mario Brothers game engine, as long as Mario is moving downward, this will be a kill. So even, for example, if Mario took a jump like this, right, and this is at the height of the jump, and he starts moving downward even just a little bit, and he collides with the side of an enemy, he will kill it and jump off of it. So Mario does not need to touch the top of an enemy. That is nowhere in the actual code of Super Mario Brothers. Okay? You do not need to touch the top of an enemy. What happens is, if the two bounding boxes are overlapping, then all that it checks is, are they overlapping, and is Mario moving downward even a little bit? So for example, if this was the Goomba's bounding box, and this was Mario's bounding box, as long as Mario had a negative speed in the X direction, then he would actually kill this Goomba. So what you have to ask yourself is that the game mechanic that you actually want to be implemented in your game? Okay? So, if it is, then implement it that way. You can copy the Mario physics by implementing that. If it's not how you want your game to be implemented, then maybe you take a slightly more complex approach, like we would in our game. So, I've put in the slides here, 3 videos, and there's about an hour and a half of watching here. Now, it's not like you're going to be tested on the exam about this, but there's 3 videos, each of which are incredible production value. This one, I really highly recommend watching this because it will give you a very acute sense of pain for what we are going to be programming in this course. So I want you to understand that even very popular, very financially successful video games like Super Mario Brothers have bugs in the engine as well. So if you go through programming the assignment and you're running into some of these bugs, then you want to watch this video because you'll realize that even the programmers at Nintendo are running into this sort of bugs. Okay, so that's a really excellent video, and it shows the world record for Super Mario Brothers being beaten in 4 minutes and 55 seconds and however many milliseconds. And it explains all the physics of Super Mario Brothers that makes that possible. And that video has such high production value that I couldn't possibly meet that production value in a slide other than just playing it, and I don't want to steal their content. So please go watch that and give them the ad revenue. This one by Pan and Coke. Pan and Coke is his YouTube videos are incredible. This guy has done essentially multiple PhD theses of work in Super Mario Brothers 64. Okay, so Super Mario 64 for the N64, the first super popular 3D platforming game. He goes over how the physics work for the walls, ceilings, and floors in Super Mario 64. And we're not going to be doing that in this course, but it's a really interesting case study in the custom physics engine that was written for Super Mario 64 and how they do things like, for example, when Mario is running along and hits a coin block, he'll be blocked by that. But if he's running along and hits a ramp or hits stairs, he'll walk up the stairs. So how did they actually accomplish that? How did they determine the difference between he should be pushed up on top of this block versus not be pushed up on top of another block, right? Or where they have rotating platforms, how did they decide whether or not Mario should stand on this platform or start sliding off this platform? And it's a really, really fascinating video. And then, of course, you can't link to Pan and Coke without the watch for rolling rocks in a half an A-press video. So this has nothing to do with the course. It's just like a super entertaining, super memey video. So all that will be in the slides for you. And for those of you out in the chat who are not in the course, I am not giving out the slides to people that aren't in the course. Only the students have access to the slides, but you can just screenshot this or go watch the VOD and type in the URL. Or go to YouTube and just type in these things. So that's the end of the slides, but I just wanted to, once more, show you the assignment and how that stuff is going to play into the assignment. So here again, this is assignment 3 that we're going to be doing for the course, okay? So here, Mega Man is running around in Super Mario World. I can jump, I can shoot. If I try and run into this pipe, I can't go through the pipe. If I'm on the pipe, then I just stay on the pipe. If I shoot, then the bullets travel for a given amount of time before they disappear. If I shoot into a pipe, it will be stopped. If I shoot a brick, the brick will be destroyed, but not the question mark if I can actually shoot it, right? If I hit a question mark from above, nothing happens other than I stand on it. If I hit a question mark from below, the coin appears, all right? And so these are the physics that you're going to have to be implementing. And again, if I turn off all the textures, you can see that we are having overlap, but the game engine updates it before it's actually displayed, right? So we never actually see the thing clip into the other thing. Actually, we do see it kind of there, and the reason we see that is because the bullet physics, you don't need to push the bullet out. You just you just destroy the bullet, okay? So these are the type of decisions that we have to make in our game. And you can see here, if I actually do collide with something from the diagonal direction, sometimes it goes on the top and sometimes it goes to the side, depending on the magnitude of that. So that's how I've written the solution, and hopefully your solution will be kind of close to that. Okay? And as a treat to everyone in the class, I've gone over time in a number of lectures in the course already. So we're 10 minutes, we got 10 minutes left, but I'm going to end it there. That's all I wanted to give out today. Next class, we will be, on Thursday, we'll be covering how we're going to actually be loading the textures into our game, how we'll be turning those textures into sprites, and how we're going to have textures that hold animations in them, and how we're actually going to do the math for all of those animations so that we can do things like, for example, make Mega Man's animation actually run in the game, and do things like the exploding brick or the spinning coin, etc. So that's what we'll be doing there. So that's it for the lecture. I'll stick around for a minute and answer some of the questions that I see scrolling by in the chat. So there's a couple of questions from like halfway through, which I don't need to answer. Let's see here. So is the chat filled with students from the university? It's probably about half and half university students and not. Are we talking about quadruple parallel universes? So that was a reference to the Watch for Rolling Rocks video, and I won't spoil it. You should go watch that video. How does making a collision exception work? Like when Mario stands on the pipe and you get into the pipe if you click down. Well, there's a million different ways to implement that, but you are just standing on the pipe, and then what you could do in your input handler is say something like, if you've pressed the down button, check to see if you're on top of a pipe which has been tagged somehow with the ability to enter it, right? And so you're not like physically entering a pipe. Mario's sprite is just going down behind the pipe, and so it's a little bit hidden. And then you get teleported to another place. And if you actually watch the first video that I linked, they actually explain all the physics behind how Super Mario Bros. 1 implements that. So one person is just asking a ton of questions. You're asking too many questions to be... Just go back and watch the lectures, okay? You don't have the context of the full course, so go back and watch the lectures to answer all those questions. Okay, cool. Well, thanks all for tuning in. I'm going to cut it a little bit short there. And I'll see you all on Thursday. Have a great day.